Do I have to unmute here or?
Make a test doing this. That should work. Otherwise, we need to.
I'm just wondering whether this is whether I have to unmute my Zoom or whether this is.
So the stream is going from the microphone.
Okay, good.
If I unmute yours, you will have a feedback.
Okay.
Okay, so it's time to start our afternoon session, and it's my pleasure to have Ingrid. Ingrid will tell us about topological picture tracking with applications to visualization.
Thank you. So good afternoon, welcome everybody. As everybody before said, it's really a pleasure to have the chance to talk here, and I would like to thank the organizers. So what I want to talk about today is some recent work that we did in my group that is related to feature tracking, to topological feature tracking in visualization applications. And I would like to start looking a little bit into what I mean with this title. So why doesn't this move? Just a second. Okay, the first thing I would like to talk about what I understand with visualization application. So my background is, this entire research of my group is located in visualization. If I would have to summarize what I mean with visualization, it's for me kind of data analysis with a human in the loop. And thereby we are especially interested in scientific applications. This means we are getting data from imaging, from measurements, from simulation, and so on. And what you see here on this picture is kind of the classical visualization pipeline. When you think about there's some process generating data, and the first step would be to think about finding a good model to represent your data that allows you to get abstraction and to guide your visualization process. And then there are further steps like rendering pictures and something that is presented to the user in the end. And what I'm especially interested in here is really this step from data to model. And this is also where topological data analysis then comes into play. But I'm also very much interested in the second part, which is also very important, that we don't have here one way pipeline, but we would like to have a possibility for the user to interact with all these stages in the pipeline. So the user can change the experiment, the user can change the model, hopefully at least a little bit, and the user can interact with the presentation, rotate, click on the data set and put queries to the data set. Altogether, as a research that we are doing, so in summary, it's about trying to help the user to understand the data, really also to build kind of a mental model of the data. So probably if we are successful with this step, visualization would not even be necessary anymore, and then we can give the entire process to some automatic solution which give you one answer. So most of our work is really application driven. And we have a lot of different applications, so for me it was not so easy to pick something that I should talk about here. So ranging from material science, from nanoscale, molecular dynamics, up to macroscopic scale and simulations in the automotive industry. I have a lot of medical applications, and something that's interests me for a long time is also the topic of kind of understanding turbulence here. But for sure, at the same time, we also try to develop generic methods, which comes to the model building that I mentioned before. And here we are looking much for ways how we can abstract the data, how we can track structural changes. And here we are using a lot of methods from topology. And for sure, we have the visual part, thinking about what are good visual representations of these abstractions that we introduce here. So what is a typical setup? In my case, we are mostly dealing with data that we call fields data. So this data given over a continuous domain. Generally, this is a really very simple three-dimensional volume plus some time. When we are talking about attribute space, This can be scalar fields, vector fields, tensor fields, or a combination of all these different data. So today I will focus mostly on scalar data in our analysis. So coming to the second part here, talking about that we are looking for topological features in our data. I want to give a very simple working definition of a feature for now. So we consider in this context a feature just as a subset in a domain, nothing else. That feature is so much overloaded term so that we at some point decided to really specify the feature to this. And when it comes to what kind of features we have, so principally this can be everything, everything that is interesting to somebody. But in many cases, these features can be described with topological descriptors, and typically we are using here something like trees or other contour trees, merge trees, which are a specific variant of the regraph. But we have such a simple domain that we only have trees here. We are also looking at persistence diagrams and also the Morse-Mel complex. Even though we have seen all these things already in previous talks, I just briefly want to say how I use these concepts. So especially in the context with visualization. So a merge tree basically records the connectivity changes of subsets if I change the level. And here a typical application would be kind of looking at an electronic field, and we change our level set and we see how the topological structure is changing, which can be nicely summarized in a tree. So in one dimension, this could look like this, where you have kind of a filtration going from the bottom to the top with a scalar field. You see, and what is important for us, what we really need here, what are the characteristics, why it's useful for us. It provides, on the one hand side, an abstraction of our data. It also gives us a hand to define some spatial features, which is very central in visualization because we want to show something in space. It also supports a multiscalar analysis, and we get a spatial segmentation here. A different representation here would be using the branch decomposition that we are also often using, where our features are more related to features tracked in terms of kind of looking at birth and death, and then we get an equivalent tree, but in a different representation, which then also directly leads kind of to the persistence diagram. So the last structure that I briefly wanted to mention that we are using is a Morse-Mel decomposition, which segments our space into a region of similar gradient behavior. And so the segmentation in the end looks like this. So altogether, I will not talk about computation during this talk, even though this is also kind of an important part of our research, because everything what we are doing, in the end, we need a working software. And in most cases here, we are basing all the computations on discrete combinatorial methods and near discrete Morse theory. So then I have some just nice pictures that I thought that I have at least to show how we typically use topology here just to get a segmentation of the space where we color an isosurface according to the segmentation. This is actually a crystal structure that is shown here and the electronic field associated to it. Or here's another example where we use kind of the Morse-Mel complex to generate a segmentation. I added this picture because we talked about this application before. We are on the one hand side here the visualization of the segmentation, but we also get kind of a connectivity network out of this. But this is not the topic of the talk. So the last part that I now have kind of in my title is a tracking. Let's briefly look what are the conditions that I need for tracking. At first, for sure, I need some feature definition. This, very importantly, is semantic meaning in our application. We need some geometrically correct correspondence between the features, between time steps, and we need some way to detect structural changes. The key challenge thereby is to find an appropriate metric to compare our merge trees, for example, or the topological descriptors, and to find a good distance measure for comparison. There are a lot of nice metrics that we could use, like bottleneck distance, Wasserstein distance, and there's for trees, the tree added distance. But most of these measures ignore completely the geometric embedding of our features, and then they are not useful really to get a spatial tracking of our features. So this led us to this actually joint work with A1, what I show now, thinking about how can we stepwise add a little bit more geometry into the picture for our purpose. So if you think about a barcode representation of your data, this is doesn't completely care about where your critical points are located in space. It only thinks that something is born and something dies. But then if you compare, don't care whether this is a left mountain or the right mountain. But these are mostly not sufficient for our purpose. So the next step then going to the merge tree, we're adding already a little bit more geometry in it. So where we kind of have some information how these barcodes are glued together, but still we don't care where the critical points are. And the next step is something that we call then a labeled merge tree, where we use to superimpose some geometric information on the leaves of the merge tree to bring more geometry into play. We also can add some gradient information that we use for the propagation, and kind of the end of the story would be that we are going back to the original field and consider the entire field and the entire embedding. So what I will mostly talk about today is labeled applications that use a labeled merge tree for comparison or for tracking. So if we introduce a labeling to the merge tree, we kind of automatically have our correspondence problem solved between the different time steps. And what information we are using for the labeling, we are mostly separating this step completely from the computation of the topology. So if you have labeled merge trees, then there's also a nice possibility to compare the labeled merge trees, representing the merge tree kind of as an induced matrix, which is kind of here shown in some way, and then you can easily compare the matrices, mostly using the L infinity law. So this works very nice if you have pairs of merge trees. But however, gets much more challenging if you have a lot of trees and you need kind of a global labeling to make this working in a consistent way often fails and introduce a lot of instability in the nice process that you have before, where you have a lot of guarantees about your topological structures, and then you are starting messing around with these labels. In the following, I will just talk about 3 different applications where we are using a labeled merge tree for some visualization purposes, and I will show you how we kind of solve this problem here. So the first application I want to talk about is cyclone tracking. Cyclone tracking is often the first step in the analysis for meteorology or climate simulation, and it's really, really important to develop models to understand how are they forming and how do they evolve over time. So generally speaking, it's a weather phenomenon where we have a lot of swirling winds. How this explicitly looks like can vary a lot depending on where on Earth you're looking or kind of what season you're looking at, and altogether there's no precise mathematical definition of a cyclone. However, in many cases, they are somehow related to some extreme values, for example, minima in the pressure field or maxima in the vortex field. So what you see here on the picture is actually the color represents a pressure field. The texture in the background represents actually the wind field. This picture comes from a different project, and the dots that you're seeing, these are actually critical points in the vector field and not in the scalar field. That we are not, I will not use in the following. So the data that we use is publicly available data. It comes from simulations, probably to give you an idea what is the resolution. So we have in latitude and longitude a resolution of 1 degree, and we have data for every 6 hours. What you see on the right, these are just a heat map of the number of cycles in certain areas of the Earth. So here you see specifically a part of the field. This is a very simple simulation. This is called the aqua planet. It's kind of the simplest configuration that we have, so that they ignore that there are any land masses. And this is kind of the first playground for us to think about what we would like to do here. These red little circles are the minima of the field. The blue circles are the saddle points. And what here would, for example, qualify as cyclones are these regions. And what you see is they often contain a lot of critical points. The depth of these regions also varies a lot. So it's not possible to have a kind of a global threshold. And even if you ask different experts, they might define a little bit different extent. So this means we need a flexible cycling definition that can easily be adapted by the domain scientists. So in summary, we are looking for a hierarchical feature structure, which has some kind of flexibility, and also that we can compute in an efficient way, so that if there are some changes, that people get an immediate visual feedback here. So how do we solve this in this case? So the features that we are using, we call them ground features. They are based on the merge tree. In the end, it's a hierarchical grouping of critical points. For the correspondence between, for the label propagation, we are using something that we call a Morse mapping, where we follow the gradient field of the next time step. And the feature tracks are kind of a combination of the first 2 steps, where we can inherit the connectivity of the features from the critical point tracks. And in the end, for us, also important that we have to have a nice visualization where people can interact with. So what is a ground feature? So this is just a drawing that we did together with our application scientists, discussing what we wanted to have. So the idea was, in the end, they would like, so here these are maxima. In our actual application, these are minima, but principally it looks the same. So we have quite dominant maxima that carry a feature, and then we just go down a local threshold and group or critical points that fall into this area together. Thereby, this threshold can be locally varying over the Earth. And in general, we do not only look at one threshold at a time, but we are always looking at a certain list of thresholds simultaneously, which gives us kind of a nested structure of our features. So looking at a merge tree representation, you see kind of this grouping of features which motivated the name kind of ground features in our applications. If you are looking at it in a persistence diagram, if you would have a constant threshold, all points that are above the red line, they qualify to carry a feature. Then you have a lot of low persistence critical points that are grouped together with this feature. For the tracking, this is just repeating the same thing on the way. There's just a picture how the merge tree would look like for the aqua planet in this simple case. This is already here a lot simplified, this representation, because otherwise this tree becomes already quite complex, and just visualizing the tree itself does not make much sense. And if we now filter away very high value minima, and then all these middle red bars represent the cyclone features that we will track in our planet. Here we see an example of one of the cyclones moving over 3 time steps. You see at the beginning we have here 3 minima, and we have 3 minima, and the third time step we only have 2 minima. And the size of these spheres represents just the persistence of these minima. And you see that kind of the geometric embedding is not stable, so the most persistent or carrying features this can jump around a lot, but the group of critical points is quite stable here. So for the correspondence, we just follow the steepest gradient here, following a discrete gradient field. There's not much magic behind it, so we are doing this in the forward direction and connect a critical point with some critical points in the next time step, and there will always be something connected. Sometimes they are not physical. These are things that might be filtered out in a later step, and we also do a backward tracking. And if you only have a connection in one direction, if they are weakly connected, and if they are connected in both directions, they are strongly connected. So thinking now about the entire time series, we start at the beginning, give a certain labeling to our nodes, which we now propagate over time, which allows us to derive these feature tracks. So this is a different representation here. Each vertical bar represents 1 time step. Each circle on the bar represents 1 minima, and then you see kind of the grouping. And on the right side, you see the feature tracks that just inherit the connectivity from the critical points here. This is a result for the alpha planet. So there's a lot of things going on. If you have the complete tracking graph of the critical points here, but if you then group your features together, then this would be the result here. So here the third dimension represents time. So you see kind of the temporal development of these cyclones, how they move over Earth. So now I move on to a real data set. So this is basically the final result that we get out here. So we have on the one hand side here an abstract representation of the tracking. So here these are the time steps in this direction. And you see that we have here, in this case, 2 thresholds that we are following at the same time. So the light gray is kind of the larger offset. It sometimes combines 2 of these tracks, and the inner parts represent the smaller parts. Here you see the embedded tracks on the Earth, and all these representations, you can interact with them. And for example, select one of these tracks and explore what's happening here. So here you see that you have a splitting of your cyclone on the if you are zooming in into a feature, but if you're zooming out, there's still computer together. But these are events that our application scientists are very much interested in, and they call this a multi-centered cyclone that we have here. And you also see kind of these tracks embedded in space. You also can augment this with a spatial region here. So we are now associated, so these balls are the time steps that we have. And these are, they are just connected over time. And you see the areas that are associated with each time step to this point. You also see that from one time step to another time step, the cyclones do not even overlap. So a matching using overlap does not work in this configuration. So in summary, for the cyclone tracking, we compute these critical point tracks, which can be really, really messy, from which we derive hierarchical features, have our augmented trees, and then finally visualization. So with this, I would like to move to the second example, which at first sight looks very different. So this is a medical example, and here's some story to tell how we came up with this application here. So these were people from the neuroscience department at the Będlewo hospital in Linköping that approached us, and that they have very complex data and that really no clue how to deal with these data. But actually, for sure, they were doing things using 10 different tools to finally get something out of the data. And the context here is something that we already heard also in the previous talk. It's kind of this brain-gut axis that they want to investigate, so that people have probably stomach problems, but the origin might be somehow in the brain. And not much is known about this disease. And they had data from questionnaires where people were talking about, for example, anxiety and depressions. And there are a lot of measurements, blood measurements, other measurements that they took for all the patients. And then, in addition, they have also field data from imaging from the brain using functional fMRI to show the brain activity. Here in the resting state. And the goal was to see, can we find anything that helps us understanding this data set? And the first step here was, really, so we always have to start with some nice visualization. So this is just a rendering of the brain where we highlight these highly active areas, but this rendering is only a small part of kind of a big system that we built, where we have here spatial presentations of the activity. And what you see down here, something that we call parallel coordinates, where each of these vertical bars represents kind of one measurement in our data set. And each of these lines here represents kind of one patient. So if you walk through the line, you get all the information for one patient. So we have here options to form groups and to do statistical comparison of the groups. You can kind of query certain axes here and see how the correlation to the brain activity of this axis. And you also can go the opposite way, so that we have here a list of a brain atlas that was given, and you will select certain brain region and get a representation what is the relation to your different measurements. And at that point, on the one hand side, they were quite happy with the system. There came the idea of, yeah, it would be so nice if you would have a patient-specific brain atlas or brain segmentation. And this is what basically inspired so the next project, where we thought we would like to have subject-specific activity regions in the brain. Then look how do these temporal patterns, how do they look like, how do these specific sites change in activity over time. So here we have been using different data. So as I mentioned, this irritable bone symptom or this brain-gut axis, people have no clue what to make out of it. So therefore, there's absolutely no ground truth for everything that we did. So therefore, we went here to a data set which has a patient is going through a very well-defined set of activities. Here, starting kind of with rest and memory, video, math. So every of these parts appears twice in a different order. So I think we have roughly 1,000 time steps here, and the entire session took 25 minutes for each of the patients. So how do we define our features here? We would like to characterize the main characteristics, so it should be highlight regions that are active in the brain. We also wanted to directly derive it from our raw data without any preprocession. The dimension should definitely be reduced in this process, and it should give us somehow a robust presentation. And what we did here, basically using exactly the same feature definition as for cyclones. So here we have kind of these activity regions in the brain. So what you see here is just one slice of the brain. You also see a little bit of the resolution of the data that we have. So you see a kind of a representation of every voxel. So what we have here is kind of a simplified merge tree where every node represents one of the regions in the slice. So if you are looking at the three-dimensional volume, this becomes much more complex. So for the correspondence, again, we used kind of the same idea of using kind of the steepest descent, so this what we call Morse matching. However, what is very different here, so we do not want to follow some changes over time, but we would rather be able to compare arbitrary time steps with each other. So this means we need a kind of a global labeling now for all our trees. And the basic idea that we have here is kind of to build up a reference frame, which can then serve as a pivot theory for comparison. And how we do this, so we are looking here at all the time steps and all the trains, and we combine them into one train that we call a reference train. And every box we take the maximum over all time steps. So this means this is a train that shows full activity in all regions that appeared over the entire time. And then we can kind of use this train to build a tree that most likely represents all the active regions, and for all time steps we will find some node that we can match it to. We use this, again, using our ground features to get our activation sites, and then we use this to generate a labeling in the individual time steps. So in difference to what we had before, where we have kind of this propagation of the label, we have now really one dominating tree that brings the label to all our time steps. What we use now for the comparison, we don't use the entire induced matrix. We will only use the values in the leaves of our trees, always the highest activity of a certain region at a certain time step. And from that, we build a big feature matrix where one dimension is spent here by the activity labels. These are roughly 150 regions. And then the second dimension is time. So what are we doing with our feature matrix now? So we have kind of different representation using kind of dimensionality reduction with respect to time. So we had a discussion yesterday evening during dinner how reliable these kind of representations are. So I just have disclaimer, take it all with care. So the first thing that we have here is TSNE, the dimensionality reduction that tries to maintain a neighborhood. For sure, it's a two-dimensional representation of a higher dimensional space. Only so much truth can be in that representation. But one thing that you can say, if you have clusters here, it's very likely that these points are already close in our feature space. What does mean every point here represents one time step of our time series, and the color represents the tasks that the person performs. And what you immediately can see that the tasks are incredibly well clustered. But you have for every color, you have two clusters. And this is when the task appears for the second time. You can observe that this is kind of a new cluster. The second time, they don't have beautiful brightness. It's hard to interpret that they are so distinct. So we cannot derive any information from this kind of representation here, but at least we see that it seems that there are some coherence within one task. So here's the second representation, shows you really the individual distances that we have with the reference frame, and the background shows again the colors. And here we have a pairwise similarity matrix. You can see some block structures. Yeah, it needs a little bit care also to represent.
Sorry, how are you presenting time in the first
this is every point represents one time step. So we basically use every, at every time you have kind of a feature vector of length roughly 120. And every of these points, which live kind of this 120 dimensional space, is now projected down to 2 dimensions. And this is a method that does this projection trying to maintain neighborhood relation. So this means, so here, the time is not directly represented in this picture. So we also could map time on these points. So we decided to map really the task of a certain time step to a certain point. So that I assume that at the beginning you will move around this area and then you will move to the next task. And when you look at different patients, so these patterns look different. For some people, they have really very clear, distinct clusters. And for other people, it looks more like a snake, so that you have the feeling that the brain continuously changes and adapts to the new tasks. And these blue dots that are all over the place, these are instruction times. So they are in between these tasks. Patients always got, or subjects always got some instructions, which are here all over the place. Yeah. So we also can do an aggregation kind of over time and look at the correlation between the different regions. So here is a rendering of some activity regions, and here this is a representation of the coherence matrix that we get out here. So the same color in this picture refers to the pink, shows pink, and yellow refers to yellow, and then you can these connections here tell you kind of the strength of the correlation to another area. So here you can now, for example, pick an area. Here is the brown area, and you see that there seems to be a high correlation with this region over here. We also have different visualizations where we aggregate kind of averages of activity over every task. See how the average for rest looks like, the average for memory, video, maths. So this is work in progress. What we did here, it shows some promising results, but we also have still a lot of open questions, and the next step is really to challenge this model and see how far we can go with this. So this ends my second application. And now my third application, again, a very different context. It's about detecting vortex reconnection. This is a collaboration with a math group from Spain that are developing a low order model for vortex reconnection. And the goal in the end is to compare their model with full-blown numerical simulations. And what we are doing so far is also work in progress, is trying to analyze the numerical simulations and get some information out of it that we can use for comparison afterwards. So this is the setup. These are actually photos, and I guess everybody of you has seen this. These are kind of trails of condensation behind an airplane that form at the tips of the wings. And at the beginning, they are really nicely parallel lines. It's actually co-rotating, counter-rotating vertices. And with the time, you see that there is kind of some fluctuation here happening. There are some waves forming. There are areas getting closer together, and at some point, you have something that is called reconnection, and they will detach after a time. And this is exactly what they want to model. They are kind of very simple. It's not simple in terms of easy to do, but in the description, in the end, it's quite a nice, simple description of the reconnection. So as I mentioned, the larger goal was really to compare numerical simulation with these models. So very interesting is so that the numerical computation, these are huge data sets. These are run on a supercomputer, taking weeks to get the results. You normally need really very big computational spaces to avoid boundary artifacts. And on the other hand side, the data that we get from this low order model, these are just some kilobytes. So comparing these things is kind of challenging. We are not so far yet that we are really comparing. So far, we are just trying to extract some quantitative information. So the first question that comes up is, how do we describe our vortices, and how do we describe connections? from a more quantitative point of view, we are asking questions about strongest vortex, when do they reconnect? And something that's also very much of interest, but we have not yet touched that, is kind of, are there any geometric characteristics during these reconnections that we could also compare with a model? So this is how a direct rendering of this data set looks like. So this is a volume rendering where we show the pressure in the field here. And you can here clearly see these blue areas. These are the vortices we are looking at, but there are also a lot of other structure, and over time the data set is becoming more and more messy. So what we now use to describe our vortices, so this is something that at least in visualization we call this extremal structures. This is a subset of the Morse complex where we connect here our minima in the pressure field always via saddle points with each other. And these cores, these nicely represent the cores of a vortex. So this is here kind of the extremal structure. All these bubbles represent the critical points, the minima and the saddle points, and all these gray lines, these are kind of extremal structures. So when we are looking here in the center, this is really what we are looking for, but there are a lot of other structures that we would like to get rid of. And what we can do at first, just from a visual point of view, now we are mapping on the diameter of these lines here, just kind of the pressure value. So we're making it thicker if the pressure value is lower, and making it thinner as the pressure value gets higher. And this is the same information that you get with color. So you see that the pressure along these structures is not constant, but it's going up a little bit, up and down, but it's really low. And this is something that we now would like to extract explicitly. And now again, looking at how these structures change here over time. You see that there's a lot of structure jumping around, but we have at the beginning quite stable our parallel vortices, which now start to fluctuate a little bit, and now they are starting to reconnect. At some point, these structures are getting detached. So what we can observe here is that these core lines, these two parallel lines, have a very stable intersection with the front and the back end of our simulation box. And now the idea is just to extract these points on the border, which are the absolute minima on the surface, and then compute the shortest path between these points along our extremal structure. By shortest, we mean topological shortest. It means we have to least climb up. So we are looking kind of for the path with the lowest maximum saddle point in between. You can think about if you have here some mountains and you want to go from this peak, you would probably go via the saddle point. And this is exactly what we are taking as a measure. How, so here is the height, what is the highest or saddle that you can take. So how deep do I have to go in fast? It's such opposite how high do we have to go? And we can solve this problem with Dijkstra's shortest path algorithm. So here, this highlights the 4 points of interest for us. So here we have the complete extremal structure, and here we are highlighting the shortest path, which gives us exactly what we are looking for. And here the connection is a little bit messy. So this one is going not the upper way, but the shortest path going down way. But this is not really an issue when we are looking now kind of at really the saddle values. And this is what you see here in this picture, where we just plot the saddle value or we call it the path bottleneck, between these different points. So we see that there's really some point in time where the pattern really changes. And here we have some which are very close. So for the red pair and the blue pair, this pair of 2 points. This is 0.1, 0.2 is blue, 0.1, 0.3 is the orange one. At some point, the distance between these points becomes really high. And this is a point that we, for now, consider as our reconnection time. We have another representation here where we show kind of these distances as a heat map, and that we also have a clear change of the behavior at some point here. So how does this relate now to labeled merge trees? So you can give the entire thing a completely different perspective. If you are really only interested kind of in this saddle point, you also could alternatively here complete the merge tree of the data set. So this is just a hand drawing. This is a real merge tree is a complete mess. But where you have our 4 selected points, which would be 4 labels in our merge tree. And the point that we are interested in here is really the lowest common ancestors of 2 point pairs. So this means we actually only have to compute the merge tree of our data set. And this would be kind of the induced matrix of a part of the tree. The only part that we are interested in, the part that is kind of defined by these 4 points. And then we get kind of a very nice quantitative measure of the behavior of the field. So this brings me already to the end. This was kind of my last application that I had here. So very different applications where we can use quite similar concepts to extract some information. So altogether, we knew it before, so topological descriptors are very powerful also in many visualization applications. Something that we definitely experience that is really important to use geometric embedding information if you want to get a true tracking, and this can cause a lot of problems. So in many cases, so if you do this labeling is so unstable, so that's kind of the distances that you compute between these matrices are so much dominated from all of a sudden flipping labels from one time step to another that can be messing up your complete results. So this labeling has to be done with care, and you have to think about what is a good method. But then labeled matrices can provide a nice solution. Yeah, and with this, I would like to thank all my collaborators. So I don't mention the people from the applications here because these are too many. Especially, I would like to thank the people from my group that have been working on these projects. This is Tala Bingmasud, Emma Nielsen, and Farhan Rashid. And also big one for kind of the base work that we did with labeled merge tree and a lot of fruitful discussions. Everything that you saw here has been implemented either in our house software in Vivo, which is the general purpose visualization prototyping tool. We have been also using PowerView for many of the topological methods, TTK, which is a topology toolkit, which is a community effort in the visualization community, which at least if you want to get first results is a good solution. Yeah, and this is I also would like to thank all of you for listening. And I'm happy to take questions.
So I think more and more people in mathematics start to realize that we do need good visualizations for science, for teaching, and that's why I'm very happy that you give it. Questions to Ingrid, please.
Yeah, first, thanks for the great talk. I'm very much interested in these labels on the merge trees. Could you say a little bit more on how you define them? So is that more of an orientation thing, or is it just more assigning names, or?
It's basically assigning names. So one thing that is at first to say, the labels must not be unique. So there can be several leaves getting the same label. And what also can be necessary if I want to compare merge trees, because in the end I need matrices of the same size, so that I need as many labels in one as in the other tree, so that sometimes we have to introduce something that we call kind of dummy nodes, kind of zero persistent nodes on a certain arc that we can use there. So you could, to get a stable labeling without any geometry, you could just use kind of something like a bottleneck distance, which implicitly gives you a kind of a correspondence between two structures. So because they are looking about, so you minimize about all possible matchings between these structures, and then the matching is picked as a minimum difference. This is one way to generate kind of a labeling. This is a labeling that is gives you quite stable results. However, in terms of geometric problems, it's often not giving you what you are actually looking for. Then people have been using kind of Euclidean distance between points and some optimization in between these. So we have been using these gradient maps between time steps, where you just take the propagation of one critical point at the next time step and just go along the steepest descent or ascent, depending on whether you have minima or maxima, and assign those to each other. This entire labeling process can be highly unstable. So we had a lot of other examples, especially in the flow applications, where we have kind of moving structures, and then it can easily happen that you overemphasize really, really small structural changes, which if you use kind of these comparison of the matrices, you take the L infinity norm between these matrices, it's very, very sensitive to outliers. So this labeling is an entire challenge in itself.
Thanks.
Other questions? Actually, I do have a question. So in this community, we're mostly looking at two-dimensional scalar vector fields. While in TDA, and we are trying to visualize dimensional data sets, really, really high dimensional data sets with tools like Mapper. Any way to kind of beat
I would not claim that visualization is only looking at these kind of applications. So this is mostly what I am doing. Since I have many applications where we have these low dimensional spaces, but there are also people in visualization dealing with higher dimensional spaces. So it also happens to us that we are getting a little bit higher dimensional spaces, but I think it's definitely interesting. I'm always sure this is probably a stupid statement, since people know more about as I do, but I'm always getting very skeptical if somebody is talking about a 30-dimensional space and tells me something about neighborhoods. I'm wondering what this actually means. So I'm too much in the feeling of this curse of dimension, that I sometimes think there's really, really a lot of magic going on. As I already mentioned, even we are using kind of this dimensionality reduction, where we go from this 100-dimensional space up to 2 dimensions. This is magic. For sure, you can optimize in a certain way to keep certain properties, but you will never be able to keep everything. Or topology.
Absolutely. Imagine the situation when it's really much lower dimensional, but also how we normally embedded.
I'm sometimes surprised how great the results are. Even there's this magic.
How about this? We'll try to convert you to this afternoon.
Okay.
All right?
Yes.
Other questions for you? Yes. No further questions. Let's try to do it again. Just to remind you, our schedule is a bit complicated today. So we have a coffee break right now, and then at 4 there are the 2 parallel sessions. Each of them contains 2 talks, so that should last from 4 to 5. And then please come back to that room because we'll have the poster preview sessions. And then the poster session is, you cannot miss, depends where it is. So this is where we meet. All right. Thank you. And let's have our coffee. So I agree with that.
Yes,
This is the data lower dimensional. What does it make a difference? Let me just switch
yes,
on the
I think it's the dimension makes a difference because there's no meaningful distance